So today we are going to talk about tables, nth terms, and next now problems. So first of all, let's talk about what a linear, a quadratic, and an exponential table might look like. Okay, for a linear table, you are looking for a common difference. So something is added or subtracted each time for the y values. For a quadratic, it's the second common difference. And we'll go through what that looks like. Okay, so first common difference to be more specific, and then second common difference. For an exponential, you are looking to see if something is multiplied or divided. Okay, so do the following tables represent linear, quadratic, or exponential? Well, first thing I look for is if there is something being multiplied by each time. So if I look at just the y's, from 2 to -6, I would multiply by -3. From -6 to 18, I would multiply by -3. And 18 to -4, -3. And again, -3 here. Because I multiplied by the same thing every single time, that's going to tell me that this is an exponential function. Okay, so number 2, we're going to first look to see, is there anything that's being multiplied or divided? Because really, if you multiply by 2, that's really easy to recognize, but some people might say, well, what if you divide by 2? Well, dividing by 2 is the same as multiplying by half, so keep that in mind. Okay, so looking at number 2 here, from 5 to 9 and 9 to 13, are we multiplying by anything there? No, we're not multiplying by anything in common. So let's talk about what changes, what's the difference between 5 and 9. So to get from 5 to 9, we would add 4. From 9 to 13, we would add 4. 13 to 17, we add 4. 17 to 21, we add 4. Okay, so because we add 4, the same number every single time, that is going to be a first difference. That is a linear function. Okay, let's look at number 3. First, I'm going to check to see if I multiply by anything. From 9 to 6 and then 6 to 5, are those going to be multiplied by the same thing? No. Okay, so what am I adding or subtracting? 9 to 6, I'm going to subtract 3. 6 to 5, I'm subtracting 1. What does that tell me? That tells me that we've already ruled out exponential, we've ruled out linear because the first difference is not going to be the same. But let's continue and see if the second difference works. From 5 to 6, we add 1, and from 6 to 9, we add 3. So now what do I mean by second difference? Let's look at these. From -1 to -3, or from -3 to -1, you add 2. To get from -1 to +1, you would add 2. And to get from 1 to 3, you would add 2. Since you now have a common change here, that is called a second common difference, so this is going to be a quadratic. And number 4, I'm going to look to see if I can multiply by something. 4 to 1, 1 to -2, those would not be multiplied by the same thing. So I say, okay, from 4 to 1, I would add 3. From 1, I'm sorry, subtract 3. From 1 to -2, subtract 3. -2 to -5, subtract 3. -5 to -8, subtract 3. Again, this is a first difference, so this is a linear function. Okay, please pause the video. You are responsible for 5, 6, 7, and 8 for tomorrow. Okay, now let's look at a couple multiple choice type of problems here. It says the first 4 terms in the pattern are shown below. Which expression represents any term in this pattern? Okay, So if this is the first term, that would be n is 1, this would be n is 2, n is 3, and n is 4, because that's the numbered term it is. Okay? So which one of these is going to work to give you this pattern here? So on top, let's test this. N plus 1. Well, if n is 1 and we add 1 to it, do we get 2? Yes. Okay, let's test the bottom. If n is 1 and we plug in 1, we get 2 times 1 is 2. Does that work so far? Yes. Okay. If we looked at b and we plugged in n is 1, we'd have 1 over 1 plus 2 is 3. Would that give us the 2 over 2? No. If we tested it here, if we plugged in n is 1, we'd have 2 over 3. Does that give us 2 over 2? No. How about d? If n is 1, we get 1 over. 3 times 1 is 3, minus 1 is 2. We get 1/2, not 2 over 2. So d does not work. That confirms that a does work. And if you want to double check, you could plug in n is 2. If n is 2, 2 plus 1 would give you 3. 2 times 2 is 4, and that does give you 3/4. So answer is A. Okay, number 10. Look at the table below. Which expression represents the output O for the nth term? Okay, so if this is the nth term, that means that this is the 5th term. So if we plug in 5 for n, we should get the output O of 15. Okay, so if I plug in 5 here, 5 plus 10 is 15, so that will work. If I plug in 5 here, 5 times 5 is 25, minus 10 is 15 here. So far we're good. 3 times 5 is 15. So far we're good. And if I plug in 5 here, 5 times 2 is 10, plus 5 is 15. So far we're good. Okay, so that means we need to move on to the next term. Let's now say that n is 10 and see if they still work. Okay? If n is 10, 10 plus 10 is 20. We should be getting 40. That means that A does not work for every term. If I plug in 10, 5 times 10 is 50, minus 10 is 40, so we can still use that. 3 times 10 is 30, but we want 40. C is not an option. If we plug in 10, 2 times 10 is 20, plus 5 is 25, but we want 40. D does not work. B is our answer. Number 11. If the first now equals 1, so this is now, which equation represents this sequence? Okay, so if this is now, the 3 is next. So we're plugging in 1 for all of the nows. So 1 times 2 is 2. 1 minus 2 is negative 1. 1 plus 2 is 3. 1 divided by 2 is 1/2. So if we plug in 1 for now, 3 should be next. C is our answer. 2 does not work, negative 1 does not work, and 1/2 does not work. Please go ahead and stop the video, and you are also responsible for number 12 for tomorrow.